So, yay, rejoice. Okay, only electrochemistry is left. Okay. So, solubility. Okay, solubility. Now we need to call upon some old skills. Okay, huh? Well, no. The old skill was called precipitate. Okay, now a precipitate can form. Okay, and you know a precipitate is a solid. Okay, however, there's some new information. A precipitate does partially dissolve and exists in an equilibrium in aqueous solution, right? So it does partially dissolve, but of course it is a solid, so it's going to go back to being a solid, aqueous solid. So I'll show you an equation here. So when we talk about our X, before it was pH, right? And before that, it was used in some sort of equation to find a K value. In this case, X is going to be called solubility. That will be the name, solubility. When I say, what is the solubility? You know you're doing a solubility problem. And X is kind of like represents the dissociation of my solid, right? But if something's a solid, it's not going to really dissociate very much. So you have to think about this dissociation as being very, very, very tiny. Okay? So, like for example, 1.0 times 10 to the negative 31 would be my X. What we're saying is we know precipitates form by adding, remember the nag-sag rules? We'll review those, but there are rules to tell us whether a precipitate was formed. And if it forms, it's going to, after it forms, start to break off and then reform and then break off and reform in dynamic equilibrium. Okay? But how much breaks off is very, very small. Okay? So if you get a large, so it's called KSP, and you definitely don't want a large KSP, but it's called KSP, it's called, so this one's got a new name too. So it's all the same stuff, but they gave them new names for some reason. It's called the solubility product. Okay. So this would be an example of some precipitate that was formed. So nag-sag except for PMS and chrome castrobare. What is the castrobare? Calcium, strontium, barium. Here's calcium. So calcium and fluorine made a precipitate. Precipitate was made, and here we have the dynamic equilibrium, and CaF2 breaks up into Ca plus 2F. Okay. So a little bit breaks off, and you make a little bit Ca2 plus and a little bit. Now here's the thing that's going to mess most of you up at some point. We got lucky during pH because coefficients disappeared. Do you see coefficients in this balanced equation? No. So is it X that I'm about to write? No. Many of you will forget that at some point, so don't. Okay, and what's that thing called? Just look at the top of the page. I call this the solubility. Right. So this question is looking for the solubility. If we write our KSP like we normally do, again, don't forget that 2. There's that 2 there. Okay, normally we have products over reactants, right? When we do these K problems. However, where's this part in my KSP equation? My expression, where's that? Why don't I have it written here? So that's the good news, is that the reactants will not be around, so there will be no denominator, and you're essentially going to have KSPs that look very similar to this. So the good news is you have a pretty simple expression with respect to just having something times something. Now the bad news is, though, is once you plug and chug these x's, what do you end up getting for your KSP expression? I should write little sp.
2x squared.
4x.
Close.
4x.
4x cube. Okay? So just don't forget that this guy here, if it's 2x, and it's squared, that 2 distributes. So it's 4x squared, and then the other x, 4x cubed. Pretty fancy stuff. So a problem like this would be fairly simple. You're giving solubility. Again, what is solubility another name for? X. So, and they're giving you the x, so they're saying calculate KSP. So you write down your equation that would represent something that is correctly electrically neutral. And then the regular old ice table. So you lose this little tiny bit. You know we lost that because that's x. And we got our plus 2x here and our plus 3x here. And then as usual, I'll just keep that up there. We have our KSP. And what's that going to be? And as you can see, these problems get kind of wacky because that's a whole lot of x's, right? How many x's is that? That's going to be 5 x's. Okay, so once you simplify all this and you work through, you basically have, so you're going to have 27 there. Okay, remember 3 cubed. Yeah, not 9, 27. And then that all goes and equals 108 x, and what the heck is that called? Quinted, squared, cubed to the 5th. And now what do we do? What are we trying to calculate? Okay, so we're not trying to calculate x. We have x. So you plug your x in. And then your KSP is a lovely 1.1 times 10 to the negative 23. That's a low K, huh?
Yeah.
So the only complicated part is just remember that solubility is X and solubility product, SP, is this equation you see here. And as usual, you're either going to find X by being given the KSP, or in this case, find the KSP by being given X. So in that sense, we should be good to go. Okay, so my crazy bipolar mess of a program has dumped the second half of this lesson. So we lost the class, and I'm just going to pick up without any funny comments from my wonderful students. Please remember to pick up the common ion effect information, pH, and solubility from your chapter outline. And I'm going to move on to the example problem, which I wanted you to redo several times. Now imagine if you had an example problem such as this one. If we read this together, it says we mix these things, okay, and we mix these things, and will there be a precipitate? Okay, that's going to be our first step. And if we remember our NAGSAG rules and PMS and Castro-Bear, we can predict that when we mix these things together, PB, which is lead, and that's the PMS, right? Lead, mercury, silver. And here we have the I, which, after we have our double displacement, we're going to have PBI. So PBI being the precipitate that is going to form, we know the KSP here will be for PBI. So the first question is, will a precipitate form? If one does form, it will be between PB and I. But with this strange question, will there be a precipitate, we're going to need to learn something a little bit that we remember from last time. And that is Q. Okay, now last time we used Q to predict whether equilibrium will shift in some sort of direction. In this case, we're going to use Q to predict a precipitate. Now, being that this variable here is pretty straightforward, just products. So it's not products over reactants, it's just products. Being that it's kind of simple in that sense, just think about products and why this number would be large or small. Now, if we didn't get any products at all, then this would be a very small number. Now, we're going to see that we have some PB and some I, given that there's these molarities here, but are these amounts large enough for a precipitate to form? Now, that is to keep in mind that if these values are very, very, very small, there will be too few PB atoms and I atoms, or ions. There will be too few of them, and they're just simply not going to run into each other. And if that number is low enough, we're just not going to have very many products. Q will be low, and if Q is low, well, then we can say there will not be a precipitate. However, we must ask ourselves the questions: low with reference to what? Well, that will be low with reference to this. So what we need to do is understand that if Q is greater than K, then the precipitate will form. Now, you really don't have to think about this too much. Just remember, if you have very few ions in solution, a very low concentration of ions, they're just going to kind of hang out by themselves. But as soon as you try and reach the saturation point with more and more and more and more ions, at some point they're going to start precipitating and creating a solid at the bottom. So, okay, but let's not go crazy thinking about this. Just stick to, if Q is bigger than K, that means we'll get the precipitate to form. If Q is lower than K, then we just don't have as many ions as we need in the solution to actually force a precipitate to form. So here's a generic equation of PBI dissociated into its ions, and then below that you can see the equation for Q, and it is the product between the two concentrations of the ions. Don't labor this too much. Just know that you need to calculate Q, and if Q is higher than K, you have a precipitate. So we need to get these values from the problem shown above. So here you see that we have 5 millimoles of PB, 2+, and 20 millimoles of I-. And also remember that we have 300 milliliters total, since we added 200 milliliters and 100 milliliters of the two different solutions. Now we are left, in summary, with 0.0167 molar of Pb2+ and 0.0667 molar of I-. You put them together to find the product, and this is your Q. Looking back at our K, we can see that the K is 1.4 times 10 to the negative 8, and our QSP is 7.43 times 10 to the negative 5th. That is greater, so we do have a precipitate that will form. So now we move on to our stoich step. Write down the equation showing the precipitate being formed. So this is a solid. 5 millimoles of Pb2+ from the previous step are going to be used. 20 millimoles of I- are also going to be included in the beaker of ingredients. We're going to lose all 5 of these because, well, they're just being used. And finally, because 2 moles of I are made for each 1 mole of Pb, you're actually going to use 10 millimoles This is your stoic step again. So 0 is left. 10 millimoles of this is left. And don't forget that we have a bunch of this made, but we're not going to worry about it yet because that's a solid. Then down here below, we need to do our ice step to finally figure out what our solubility is. The solubility will be represented by this X over here. And do keep in mind, of course, that this is plus 2x. So we need to do this equation here after doing our stoic step. We do our stoic step to figure out what happens between these two. We have our solubility being made. Now we make our ice table with our solubility, with the 2 actually down there. And this ice table will tell us how much x will be made and giving us the answer. So we take PB, which starts off at 0. Normally, I also would start off at 0 on a solubility problem. But in this problem, because of the ingredients that we use from the very beginning, we have some I left over. And that was why we did the stoic steps. You always want to make sure that there isn't anything left over. If PB and I are used together, the same amount, then we're going to start with 0 for both of these steps here. But there's I left over from the stoic step, so we need to put that I down here. And here you can see we have our 0.33 molar, we have our plus 2x, then we fill in the rest of the chart. And then we can just solve the rest of the problem as usual. Now, you know, of course, that we are able to estimate that x is very small, so we can conveniently get rid of this since that x is small compared to 0.033 molar. And then we can set up our expression. Here in the circle, remembering the square, of course. And here's the 0.033 and the original x from down here, my original k, and in the end, you're going to have your x, which in this case is Pb2 plus. Now remember, your concentration of Pb2 plus in solution is 1.3 times 10 negative fifth. That's your x. However, I, which normally would be the same number, is not this same number because we have this excess here from this step, So the answer for I, actually, you will have 0.033 molar, I minus, but the solubility is still 1.3 times 10 negative fifth.